Okay, in this video, we discuss linear approximation. So the basic idea is that we're going to use the tangent plane to approximate function values near some specific point. So to get an idea of how this proceeds, let's go back to the diagram of the tangent plane. So the idea is that here at this specific point where the tangent plane meets the graph of the function, the z-coordinate of the tangent plane is exactly the same as the function value. However, if you move away from this point, but still stick to points that are very close to it, so like say these nearby points around it, then the z-coordinate of the tangent plane is now different than the function value around this point. However, the z-coordinate is still close enough to the function values such that we can get a good approximation. So that's the basic idea behind the linear approximation. So essentially, because we're calculating z values by using the tangent plane, you'll notice that the linear approximation formula is exactly the same formula as the formula for the tangent plane. Okay, so let's take a look at example 2, where we're asked to calculate a linear approximation of this function at this point that's close to 0, 0. So because we're essentially using the tangent plane to do the calculation, most of the procedure follows exactly what we did for for example 1. Okay, so the specific point that we're using, so AB is this point here. So let's label the coordinates here, A and B. And okay, so again, we need to set up the tangent plane. So we calculate the partial derivatives. So the partial derivative with respect to x. So the derivative of this term is 2. And then here we should use the chain rule, right? So the derivative of the exponential function is exactly the same exponential function, except we have to multiply by the derivative inside. So again, we're differentiating with respect to x, so the derivative here is 2x. Okay, so let's rewrite this. So we get 2 plus 2x e to the x squared minus y. And then again, we need to calculate it at the point AB. So let's plug that in. So we get 2 plus 2 times 0 e to the 0 squared minus 0. But this term we're just multiplying by 0. So this whole term goes to 0, and we're just left with 2. Okay, so now the partial derivative with respect to y. So x is a constant, so this whole term goes away. And then the derivative of the exponential function is the same exponential function. But I have to do the chain rule, so differentiating inside. This is just x squared, so the whole thing's a constant. So that goes away. And then the derivative of minus y would be minus 1. Okay, so you get minus e to the x squared minus y. And then just like before, we have to plug in AB, which is which in this case is 0, 0. So we get minus e to the 0 squared minus 0. So this is just minus e to the 0. And e to the 0 is equal to 1. So you get minus 1. Okay, so so we need one more thing before we set up the linear approximation, right? So we have we have a, we have this, we have b. Now we also need the function value at a, b. So let's calculate this. So f of a, b, what is this equal to? So I'm plugging in 0, 0 into the original function. Right, so that's 2 times 0 plus e to the 0 squared minus 0. So this is 0, and then this is just e to the 0, which is equal to 1. Okay, so finally we can write down the linear approximation. Which is, so this is the partial with respect to x, so and then we have x minus a, which is 0, and then the partial with respect to y was minus 1, and we have y minus b, which was 0, then plus the function value, which we calculated was 1. Okay, so we get 2x minus y plus 1. Okay, so now finally, so that's the linear approximation formula at this specific point, and then now we want to approximate the function value at the point negative 0.01 comma 0.01. So instead of calculating with the original function, what we're trying to do is to use the linear approximation. So we plug this into L of xy. So just plug this into here, and then what do we get? So 2 times negative 0.01 minus y, which is negative 0.01 plus 1. And so just calculating this, what is this? Negative 0.02, and the negative, it becomes a plus. So 0.01 plus 1. And okay, so just calculating this, I get 0.99. Okay, so that's what we get as the approximation. So I mean, the idea is that the linear approximation is a linear equation, so that these are typically very simple to calculate. But with calculators, I mean, we can just calculate with the original function. So so let's just compare the actual value. So 2 times negative 0.01 plus e raised to the negative 0.01 squared minus y, which was also negative 0.01. Okay, so this is the actual value of the function at this point, and you can see that our linear approximation is fairly close to it. I mean, you might ask yourself, okay, so if we can just calculate things with the calculator, what's the use of doing the linear approximation? So I mean, in this specific instance, I mean, if you have a calculator, maybe it doesn't really make sense to do this. But the general idea of doing linear approximations, where you're replacing something that's non-linear with something that's linear and much simpler. So this is a common theme that's used a lot when you're trying to do complicated numerical calculations. Okay, in any case, this is the answer to this linear approximation example.